Next up, we have Michael Moore, Principal with Partner Solutions and Principal of Partner Solutions and Technology with NEO4J, one of the platinum sponsors for our event today. And he's going to be talking about carbon tracking and analysis with their graph data platform. Michael is trained as a scientist with over 20 years experience delivering high-value enterprise analytics solutions and portfolios for startups, agencies, and Fortune 100 companies. He has been working with NEO4J graph databases and graph analytics since 2013, and in his most recent role, he established EY's national consulting practice in enterprise knowledge, graphics, and AI. Prior to EY, Michael was at Microsoft, where he managed a global portfolio of over 65 applications in the connected sales and marketing space for Microsoft's B2B and partner ecosystems. And he's based in Redmond, Washington. Michael, welcome.
Thank you. All right. Should I shut this one off? There we go. Okay, does that sound better? All right, excellent. Yeah, so today I'm here to share with you a little bit about how to use graphs to help manage carbon. And so what we're going to do today is I'm going to talk a little bit about carbon tracking and graph databases, what they are. We'll drill a little bit into the Neo4j graph data platform. And I'll crack open a demo. It'll be a movie. And then we'll close with some comments around scalability because this is actually a really large data space. And so graphs are the up and coming way of managing data in a modern approach. Gartner is very bullish on graph analytics in general. And they even in November pointed out that graph technology is one of the 4 leading tech trends of 2022. With regards to carbon, I wanted to point out that there's been some interesting work around carbon disclosure versus non-disclosure. And you know, the opening comments and a lot of the commentary throughout the morning session is really underscoring this, which is that companies that disclose voluntarily their efforts around managing and mitigating carbon emissions have higher valuations. And you know, this is a really important point, and it's a good motivator for being able to jump on board and drive corporate initiatives around creating transparency in terms of carbon management. So how do you actually enable change? And from our perspective, this very quickly gets down to point sources and infrastructure. And you have to have contemporary knowledge of what your infrastructure looks like, and you have to be able to relate that to emissions measurements. And graph databases are a great way to do that. And so I want to take a couple of minutes and talk about what are graph databases. So I think everybody's pretty familiar with a traditional database. SQL style databases, they were invented about 45 years ago. You have a table. The table has rows and columns. Where they intersect, that's called a field. And you use it basically for storing and retrieving data. And you can do some joining across those tables using keys that are embedded in 2 tables that are related. Now, the challenge with that is that because those joins are computed at runtime and they use up server memory with every new join you compute, you can actually only do a relatively small number of joins. And it also becomes very difficult when you're trying to look at, say, a table that has billions of records in it. And so therefore, folks decided, well, you know what, we want to be able to analyze billions of records. And so you saw in the 90s a move towards big data technology and distributed computing systems and the emergence of large-scale OLAP platforms like Hadoop, where now I take my data, I shard it across a bunch of servers, and then I can take that aggregation operation or whatever it is, and I can execute it independently on each one of those servers and bring the results back, and now I can give you an answer. Challenge with that, though, is that because I've sharded the data across all of these servers, now I've lost the context. I don't actually know how the data is connected anymore. And so this brings us into the world of graphs. And so what a graph is it's a data format where records are connected by what's known as a relationship. And if you want to get technical, sometimes those records are called vertices. We call them nodes. Sometimes those relationships are called edges. The key point here, though, is that those relationships are first-class citizens. They are actually stored on disk. They're stored in memory. Each one of them has an ID. They can be characterized and typed. You can actually put data on them, like timestamps, measurements, et cetera, probabilities. And so what a graph database then does, like NEO4J, is it basically takes your data and it constructs a whole fabric of interrelated records. And because all those relationships are stored on disk and in memory, it's lightning fast. And the way the queries work is they just chase around and they traverse the data. And so what you get out of NEO4J is almost the best of both worlds. So you have the ability to store and retrieve records, you have the ability to do analysis, and you have the ability to look at all of your data in its actual context. And we scale out to millions and billions of records quite easily. So let's dig a little bit deeper into what exactly is a graph. And so a graph is a data structure that is composed of nodes and relationships and properties, which can be, think of those as fields, if you will, like you would have in a traditional database, that are stored either on the nodes or the relationships. And so if we take a simple scenario, say I have a graph, and this graph has two entities in it. It has people and autos, right? So I have a person node and I have a car node. And our nodes are basically sets of records. And I might have, in this particular graph, I have a node for a person named Dan, and I have a node for a person named Ann. And guess what? Dan is married to Ann, and Dan also lives with Ann. And you can see what's happening here in this graph. It's a very, very simple graph. It's a common graph that we all actually, a lot of us inhabit. But you can see that the semantics are different, right? I have two relationships. Each one of those relationships carries a different meaning, right? So, just because Dan is married to Ann doesn't necessarily mean they live together, or just because Dan lives with Ann doesn't necessarily mean that they're married. But with a graph, I can actually very compactly and elegantly represent both of those concepts with two relationships. Is everyone following along? So now let's go into some infrastructure. So they have a car. And guess what? Who owns the car? You should be able to read it right from this graph. Yeah, so Ann's raking it in. She's the one that bought the car. And who's driving the car? Dan is, right. Okay, and so now you can see we've got some additional semantics. And so this is basically the idea behind a graph, is you've got this persistent structure that shows how data is related. You can also see that you can put, key value pairs, data points on those different nodes, like their birth dates, or how long Dan has been driving the car, or what the car actually is. Okay? All right, so now let's quickly get back onto topic here. So if you look at carbon management, carbon emissions come from a variety of sources. We have natural sources and we have human sources. Within the natural sources, you have ocean-atmosphere exchange, you have respiration and decomposition, volcanism. And of course, ocean-atmosphere exchange, constitutes the largest volume of carbon emissions and consumption in the carbon cycle. And then you get into the human sources, and you have things like fossil fuels, changes in land use, and industrial processes. And our focus here is on industrial processes. And so if I was to think about the kind of data I need to manage carbon, I very quickly am talking about infrastructure, right? I'm talking about basically from well to flame. And within my infrastructure, I have facilities. Within my facilities, I have equipment. Within my equipment, I have sensors. I have sensors that are throwing off data. And now I have an analytical problem. And I think you're starting to see the graph that's beginning to just naturally develop around this topic. And so we think of those kinds of graphs as basically digital twins. And so a digital twin is essentially a virtual representation of your physical reality. And as you think about managing carbon and how you're going to organize the data, be able to analyze, query data, look at it at scale, very quickly you start to build up data sets that are digital twins. And the proposition that I'm going to make to you is that a graph database is an excellent way to manage your digital twin data. It's an excellent way to link all of those sensors back to the equipment that they're on. It's an excellent way to be able to query for common things like a vendor or a particular contractor or a particular model of a compressor, for example. And so if you think about digital twins more broadly, typically what you'll see is, there's some kind of a canonical model where basically sometimes this is in manufacturing, this is called a bill of materials. It could also be, an infrastructure plan. And then you have how it was actually implemented in the field. A lot of times you'll have different instances. So even though there may be a general way of building out a well pad with typical equipment, each individual well pad is going to have its own variations and its own essentially instance or representation of the choices that were made during installation. So I think of that as the as-built part of the digital twin. And again, that is also represented as a graph. But then to understand that infrastructure in a broader context, very commonly you will need to bring in a whole variety of other data. So you might have metadata about when that well pad was put together, who worked on it, how long it's been in operation, has it been plugged, is it still active, et cetera. You might have all of the various documents and drawings and assets related to that. And then you'll have a whole ton of sensor data if it's still active. And you want to be able to bring all that data together in a common structure so that you can understand the context so that you can actually analyze that and do the appropriate decision support. And so here's an example of a graph built around a well pad. And the turquoise dot right there in the middle is the well pad. And you can see here that we have a number of different assets, including things like the wellhead itself, free water knockout, water tank, heater treaters, oil tanks, the compressor. Each one of those has one or more sensors hanging off of it. And so what this graph gives you is essentially a very accurate and flexible way of representing every single instance of your infrastructure. And you can query this graph and I can say, show me all of the well pads, where there's a sensor event that exceeds some value. Right? Show me the contractor who put that in, right? Show me its geographic location. And so with a graph database, like NEO4J, we can scale out to billions of nodes, and we can handle all of the complex hierarchy that naturally emerges as you try to manage carbon emissions and at the infrastructure level. And so you can do things like create asset maps. And here, what you're seeing, all these bubbles and lines, these are a way of visualizing the graph, and I'll show you a couple more visualizations in just a second. You can look at dependencies and say, where are they? What systems are using, say, what model of compressor, if we know that that compressor is problematic. I can say, what things are next to each other? You can actually use a graph, you can map out all the piping and all the upstream and downstream dependencies in a flow pattern because the relationships have directionality. Okay, so the demo that I want to show is built around understanding fugitive methane. And so I think everyone is aware that there are new rules that are likely to be implemented. That one of those is that there will be a limit of 10 kilograms per hour max for infrastructure, and that's going to be, that's going to be a challenge. And so the data that I'm showing you is based on aerial surveys. There's about 2,400 wells. This is in the Permian, so it's New Mexico and West Texas. And you can see there's a visualization in the lower left that shows the flight paths. And so the scenario that we've got here is we have light aircraft carrying methane sensors. They're circling over production oil fields and gas fields, and they're making measurements. Now, how do you relate those kinds of measurements that are being taken at an altitude anywhere from like 1,000 to 3,000 feet down to what's actually happening on the ground? Where do you send the technician to? It's actually kind of a tricky problem. And so if we jump into NEO4J, and so this is our interface, and I'll open up a database here. And so I'm just going to narrate this little movie. And so this is our integrated development environment. We call this our Neo4j browser. And so I've got this graph here. It's got about 10,000 observations in it, 2,400 wells, and about 500,000 relationships. So when I click on a node here, the circle represents a single record. You can see on the right, these are leases, for example, various leases. I can expand one of these leases and I can see what county it's in. And I can also see what well might be part of that lease. And so just like with Ann and Dan, right, very simple. But if we scale this out a little bit, I can write a query, and this is our Cipher query language. It's very SQL-like, and you can say I'm basically going to find operators and the wells and sensors that are, or sensor measurements that exceeded 10 kilograms per hour of methane. And so here, for example, are a bunch of wells operated by Devon. And you can see the sensor measurements in red and the various wells in yellow. And you can also see how all of this is being represented as a connected data fabric. Okay, so that's the visual view of this. But I want to point out that this is a real database. And you can run typical queries just like you'd expect with any other database. And so here is a report, basically this same query, but now we're going to order it by the operators with the most wells that exceed that 10 kilogram per hour threshold. And now you can see there's about 172 records. And so this would be the kind of data that you could distribute through an API or into a BI report or whatever you wanted. Okay. So let's look at another tool we have. This is called Neo4j Bloom. This is a visualization tool. One of the first things that we'll do here is we'll just go grab the schema that's actually driving all of these reports that you've been seeing. And so the basic schema here is I have a well. That little curvy arrow, we've computed all the inner well distances in this graph. And I'll show you why in just a second. We also have the operators, the previous operator. There's history behind this data. And of course, you saw the leases and the counties. So now let's go pull up the whole graph of wells that exceed that 10 kilogram per hour threshold. And in this tool, we're pulling back about 6,000 records. And while this is kind of building, the frame rate was a little slow in the movie here, so you forgive me. But you can basically see what's going on here, right? This is actually a whole pile of highly connected data. I know it looks a little bit like a mess, but we can actually drill into this. And the reason that this is interesting to us is because all of those connections are creating context for single data points. Every data point that's in this graph is connected to something else that helps that data point be made understandable. And so we'll drill in, zoom in a little bit here. There's kind of a mapper thing that you can drag around. And so now you can see different parts of this graph, and you can see the different measurements. Yellow, is problematic. Red exceeds, and then the pink, dramatically exceeds that 10 kilogram threshold. You can see all of the different operators here and so forth. Okay, so that's great, right? So you get an idea of really what's happening with the whole structure of this graph. So now, but let's filter it down a little bit. So let's pull up what I'm calling the hot wells for BP. And now we're looking at a little subgraph. So this is BP's view of the world in this data set. And now you can see that we've got a couple of locations where they've got some production going on. You can see that most of their wells are, are within compliance or close to, but there's a few hot wells here. And so if we drill in and look at a couple of these, we can go look at one of these state wells, I think they're called. And so let's see, this will happen in just a second. Yeah, there's that one. So I can drill into this well, and this one's called State Caldwell. You can see that there's been a couple of sensor measurements in the 700 range. That's quite high. And so now the question becomes, if I want to do something about that measurement, keeping in mind that that measurement may have been made at 3,000 feet, right? I'm not actually certain that it's that specific well. And so maybe what I want to do is equip my technician to go out and say, okay, not only go look at this one well, but let's go look at some other wells that are within a certain distance of that well. And remember, I told you we computed all the inner well distances. And so now we run that query, and then and here you can see we have a relatively plain language interface. So get wells within 2 miles of State Caldwell 57. And now you can see there's actually 5 other wells that are probably, 5 other well pads that are probably worthy of inspection relative to these airborne methane measurements. And so that's just a very simple example of how you can use a graph to create context. You can do analytics on it, and you can actually use that to make operational decisions that will improve your efficiency around managing carbon. And so with that, we'll go and talk a little bit more about NEO. And so now that you've been exposed to the wild world of graphs, I want to give you a couple of constructs for how you think about whether or not your data really does fit in a graph. And so there's a couple of basic data shapes. So one common one is what we call wide data. So I have a single entity and I have a bunch of data around it. So that's basically what I was just showing you, right? The well pad is the single entity, and we're aggregating a bunch of data around that. Oftentimes you're looking at data that's very complex and interrelated. So for example, if I had an infrastructure digital twin that was actually showing flows, maybe say at a refinery or something like that, that would be an example of something that's very complex and interrelated. Hierarchical and recursive data, another great graph problem. It's very difficult in SQL systems to be able to analyze hierarchical data, because oftentimes you have to do what's known as a self-join, where you have to take a table, make a copy of that table in memory, and join every record in that table to the copy so that you can actually understand parent-child relationships in that table. And in a graph, you just lay out the data in a hierarchy, and then you can traverse it efficiently and effectively. And so for things like, I was involved in some capital projects work using SAP's capital project module, 16 levels of hierarchy for large multi-million-dollar projects. Very difficult to work within those hierarchies. You move it into a graph, it becomes very easy to do things like say, how much are we paying for scaffolding, or what is a journeyman electrician costing us, or what is this service company charging us across a suite of projects. Another thing that graphs are commonly used for is data unification, either of legacy data or data that's already been centralized in a data lake, but not yet conformed. And you put a graph on top of that, you can promote important structured data into the graph, and you can bring in the metadata for all of your unstructured data. So you can point back to things like digital assets, diagrams, drawings, well logs, imagery, et cetera. And then finally, there's hidden data. And so hidden data is where you're actually using the graph to perform inferences. And so this would be things like detecting fraud, making recommendations, determining communities or commonalities, basically identifying either common or rare patterns in the graph and drawing up new relationships that bring those forward. And there's a whole world of graph analytics built around that. So we like NEO because is highly scalable. What you'll typically see with SQL systems is that the more joins you try to do in a SQL system, the worse the performance gets. But Neo4j, the way we're architected and the way that all of our data is connected, it's actually a very low-cost operation to chase a cursor from a node to a relationship to the node that it connects to the next relationship, and so forth. And so you can have a graph that will have billions of records in it. And as far as that query is concerned, it's only looking at what is locally connected to whatever node that query started at. So it's very, very fast. We also scale to really large volumes. We have a, this deck will be circulated, but you can take a look at some of these projects. We've got a GitHub project out there where we built a sharded graph that has about 1,100 shards and was holding 280 terabytes of data. And this was done on AWS. In terms of digital twins, sensors, all of this, what you'll typically see, this is an Azure example, you'll typically see Neo4j being used as the repository for organizing and unifying data. And it's not uncommon that there'll be some kind of a hot path where you're coming off your sensor system, you're raising alerts immediately, but then there might also be a warm path where the sensor data is being processed by, say, a time series database. Like in this case, it's Azure Time Series Insights. Events are being raised, and those events are then being brought into the graph as transactions. And then you can also see in this architecture that other types of data are being referenced by the graph. And on top of the graph, you're able to do things like visualizations, put on various kinds of BI reports, or open it up to your data scientists for analysis. We also support a whole number of APIs and drivers for Java, JavaScript, .NET, et cetera. And so it's very easy to build custom applications on top of Neo4j. Here's an example of a Power BI report using Neo4j. And so we have a ODBC driver that basically can take a graph, flatten it, and present it to Power BI for reporting. And so a lot of your users won't even know that there's a graph operating behind the scenes, right? You just flow in more data and it'll look richer, you'll have more filters, and you can do more interesting things with it. And then finally, I want to just mention that we have a very powerful graph data science library. This is one of our most popular products among the data science community. And there's a whole trend now of using graphs to do things like feature extraction, embeddings, et cetera, to actually improve machine learning models. And we have about 65 algorithms covering a whole variety of topics. And all of these analytics are actually performed in the same environment that the graph is sitting in. So it's actually a very tightly coupled analytical environment, and it doesn't have this very long, kind of workflow where data has to get, exported out to something else, get worked on, and the database has to be rescored. This is all handled very tightly and closely. Okay, and just to close out, Neo4j, we are a startup, but we've been around for quite a while. We're widely used. We just closed a very large round of funding, the largest in database history. We have a giant developer community of over 200,000 developers. So if you work with Neo4j and work with graphs, it's not difficult to find people to actually build those and develop those for you. And so, and we're already working with a number of oil and gas and energy services companies. We are the leader in the graph database category. And also if you go look at this same website, this is called dbengines.com, we're also in the top 20 of all databases now. And more broadly, besides carbon tracking and monitoring, you can use Neo4j for, all of your digital twin, predictive maintenance. I mentioned capital projects, data unification, identity management, supply risk, dependency, distribution, a lot of regulatory compliance use cases, audit, HR, and fraud detection. These are all common use cases. Okay. And so the key points that I want to make is I think it's very difficult to operationalize a carbon management program without having a very good understanding of the current state of your infrastructure, which very quickly leads you to digital twins, which leads you to a whole pile of hierarchical data, which is actually best naturally represented in a graph. So that's that's our point of view. If you put your data into a graph, you'll have a structure that you can quickly analyze, and it'll help you drive that decision support in a way that will help you actually take proactive action. We can scale to very large data volumes, and because we're an in-memory database, we're super fast, and so you can actually run your you can think about running mobile applications, put the data right in the hands of your field engineers, technicians. So there's a lot of utility there, and so our point of view is basically we think graph technology offers the analytical power to meet the compliance needs that are ahead of all of us and release real business value along the way. So thank you. All right, we have a couple of questions here. So let's see, how well does graph database integrate live with existing systems of record? It actually integrates very well. So NEO4J is ACID compliant. It's used widely in the financial services industry. And so you can bring in sensor data directly into the graph and load it. The only caveat I would say there is that it probably doesn't make a lot of sense to bring in a ton of raw data. It's probably better to bring in events and excursions and exceptions. If I was to deploy Neo4j for my organization, would I have to manually plug in all my data point by point? No, you don't have to manually plug it in. We have a whole bunch of support and connectors where you can basically have an ETL tool, for example, running jobs that are populating your Neo4j database. Let's see, is there a proprietary query language? There is a query language. You saw some examples of it. It's called Cypher. Cypher is actually the basis of a broader language that's called GraphQL or GQL, which is likely to become the graph standard, essentially just like SQL. And you'll see it widely adopted by a lot of platforms. So I think it's a great thing to learn Cypher because that'll get you equipped if you're a database developer for this whole next wave of graph analytics. Thank you.